So I guess a good name for what I'm doing is condensed group cohomology. So there's two parts to this. There's condensed and there's group cohomology. About this, I will say a few words at the end, but not so much because I think sadly it's a little bit inaccessible. I don't think it's very interesting if you don't have a lot of background. So I will talk about group cohomology, and in fact, I will also break this part into two. I think I will talk a little bit about cohomology first, and then about group cohomology. So cohomology was born for topological spaces around the 30s. And actually first there was homology. So if you have a space X and some module that I will not say what it is, you can just think about the integers, for example, or R. So to this you associate a lot of abelian groups. In fact, one for every natural number. And you call this the nth homology group of X with coefficients in M. And the point is that these homology groups are algebraic invariants of the topological group. So of course in topology a big problem is understanding when two spaces are isomorphic or at least homotopy equivalent. And if they are homotopy equivalent, then they will have the same homology. So this is why it was interesting at the beginning. And then they also realized instead of only looking at homology, you can also look at the dual, which means like inverting everything that you've done, like all the arrows and everything. And you get another chain of abelian groups, which are the cohomology groups. This is the nth cohomology group of X with coefficients in M. And it turns out that cohomology brings a lot more structure than homology. So this is why it was interesting. So for example, you can combine, once you have all the cohomology groups, you can combine them into a huge thing that will turn out to be a ring. So again, you have now like way more structure than you did in homology, and this helps differentiate certain spaces. So for example, the product of two spheres and a wedge of spheres they cannot be differentiated from the point of view of homology. They have the same groups. So you might think they are homotopy equivalent, maybe you don't know, but it turns out their ring structure is different. So I think this one has a trivial ring structure and this one doesn't. Maybe it's the other way around, I don't really remember. But thanks to cohomology, you know that they are not homotopy equivalent.
So this is always like the only known way to differentiate things by looking at their algebraic invariants, right?
I don't know if it's the only way, but it's the only way I know.
Yeah, well, at least the first way people come up with.
Yeah, exactly. It's always what you first look at.
Yeah.
Because the homotopy groups are extremely hard to compute, so homology and cohomology are usually easy.
Yeah.
Yes. Okay, so this is, of course, there's also a very interesting theorems in cohomology. So for example, Poincare duality allows you to relate the homology and the cohomology of a compact-oriented manifold. I don't know, there's a lot of tools arising from cohomology. So this is the topological point of view, but I'm doing group cohomology. Mm-hmm. And of course, a group is an algebraic structure, so you might be thinking, how do you do this algebraically? Yeah. And in fact, it first arises from topology again. So in 1936, Hurewicz introduced aspherical spaces. And these are spaces whose homotopy groups are all trivial, except for the first one, except for the fundamental group. And he realized the homology and, well, the cohomology of this space depends entirely on the fundamental group. So if you call this G, then it makes sense to talk about the cohomology of G. I will write this. When you talk about the cohomology of X, because it depends entirely on G. So by this point, for certain groups G that arise in this way, you have a cohomology, but what if you don't have such a group G? Then it turned out someone else realized that there is a spherical space and aspherical. With fundamental group G for every single G.
Wow.
So with this, you can already define the cohomology of a group. And this one is constructed with a CW complex whose, covering space is, how do you say this? Contractible, sorry.
No problem.
Yeah. Okay. And so then we already have a cohomology for a group. But this, again, is very topological, and a group in the end is an algebraic structure, so this is not very convincing. So then what you can do is to build a chain complex, which in each degree looks at maps of sets from Gn to the module that you have chosen. And in this case, for group cohomology, a module is an abelian group on which G acts. So you have a group G, you have an abelian group with an action of G on it, and then for every degree n, you can look at the maps of sets between G to the power of n to A, and then build some quotients, and you get a cohomology, which is the same one as this one, and this is the classic cohomology. And of course, it's nice, but it doesn't take into account any topology, because the thing is, you can have a topological group, and then what do? Now you're only looking at the algebraic structure, you're missing all the information that comes from the topology. So then you can think, okay, instead of looking at just maps, I will look at continuous maps. Then I have the topology into account, and of course you can do this, you get another cohomology, but it has some problems. So this is called continuous cohomology. So there's like 3 axioms that you want a cohomology to fulfill, and there's one of them that this one doesn't fulfill. I cannot enter into detail, but this is a big problem here. And then it's trivial in cases in which you wouldn't want it to be trivial. So for example, trivial if G is connected and A is discrete. So in this case, you don't get any information from the cohomology, so still not perfect.
Yeah.
Then there's a cohomology that is measurable cohomology. And this is very nice. It looks at measurable maps. This fulfills all the 3 axioms I mentioned before, so it's a very nice cohomology theory. But the problem is it's a little bit hard to compute because it relies on very hard analysis. And also you can take G can be any locally compact groups, which is nice, but A must be a Polish space, so not just any locally compact group. So it's still not what you would like.
Yeah.
Then there's also something called bounded cohomology. It also has very, very nice properties, but it's extremely hard to compute. Like I'm talking up until 2 years ago, I think, there was not a single group for which this bounded cohomology was known unless it was known to vanish everywhere.
Yeah, okay.
So still not very useful. Okay, so this is the setup we have. And all these problems come from the fact that the category of locally compact abelian groups is not an abelian category. So there's not a straightforward way to do cohomology there. So that's why you have to make up all these things, and there's some problems.
Yeah.
And this is where the condensed part come into play. Because the category of condensed abelian groups does form an abelian category. So there should be a straightforward or like some way of doing cohomology there. There's a lot more of structure. So you can build more quotients and more things are allowed. So this is the idea of my work, to do group cohomology in the condensed setting. Now, what is a condensed setting? I won't say much about it, but a condensed group is not a group, but a functor. And the way I like to think about category theory is that when you look at a group alone, you're studying just the behavior of this group as an individual, and maybe you cannot get much information out of it. But if you look at the category of groups, then you look at the way groups interact with each other. So this is kind of the gregarious behavior instead of the individual behavior.
Yeah.
And sometimes you can get very useful information out of it. Like, I think of this more or less like when you start studying linear algebra and you study matrices and they are just like a box with a bunch of numbers and you can multiply them and they have some properties and blah, 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 blah. And then you go to abstract algebra and you see that actually these matrices form a group. And from the fact that they all form a group, you know how they interact with each other and you get information from them.
Yeah.
So I think this is a little bit a way to understanding why category theory is useful.
Yeah.
And this is all I had to say.
So do you then want to compare your condensed group cohomology with all the other approaches you listed?
Yes. So there's some ways in which you can turn an abstract group into a condensed group. And depending on the way in which you do this, we think we will recover each of these.
Each?
I mean,
Yeah,
maybe. This was the original goal. I already know it's not going to be exactly like this.
Yeah, of course.
But like in some similar way, you can recover them. Yes.
Okay. Cool. Thanks a lot.
No problem. Thank you.